Hello and welcome back to HK Academy. Imagine your converter is switching at 200 kHz. That gives your microcontroller only 5 microseconds to sample the signals, execute the control algorithm, update the PWM outputs, and get ready for the next switching cycle. But how do you know whether those 5 microseconds are enough? How can you tell if your software is close to reaching its computational limits? In this video, I will explain what CPU load really means in digital power electronics, how it is calculated, and why every embedded control engineer should understand it. This video is also the first part of a new series on CPU load and real-time software design for digital power control, where we will gradually build from the fundamentals to practical implementation and optimization techniques. Whenever we implement a digital controller, all computations are executed by the microcontroller. The ADC samples the converter signals. The control algorithm calculates the new duty cycle. Finally, the PWM module updates the switching signals. At first glance, this seems straightforward, but there is one important limitation. Every calculation takes time. On the previous slide, we saw that the microcontroller is responsible for sampling the converter signals, executing the digital control algorithm, and updating the PWM outputs. But how do we determine whether the processor has enough time to perform all of these tasks? Let's answer that question using this timing diagram. In this example, the PWM module operates in up-down counting mode and generates complementary gate signals for the high side and low side MOSFETs. For simplicity, let's assume that the ADC samples the output voltage when the PWM counter reaches its peak value. Of course, the ADC requires a finite amount of time for sampling and conversion. Once the conversion is complete, the ADC interrupt service routine is triggered. Inside this interrupt, the microcontroller first reads the converted ADC values. Next, it executes the digital control algorithm. Depending on the application, we may also perform software protection routines, communication tasks, or other application-specific calculations. Finally, the PWM compare registers are updated so that the new duty cycle is applied during the next control cycle. Once the interrupt finishes, the processor may execute another interrupt, continue running the background loop, or simply wait in the idle state until the next interrupt occurs. For simplicity, throughout this video, we will assume that the CPU remains idle after the interrupt has finished. Throughout this video, the term CPU load refers specifically to the execution time of the control interrupt, since this is typically the most time-critical part of a digital power control application. The overall CPU utilization of a complete embedded application may be higher because it also includes additional interrupts, communication tasks, DMA transfers, and background software. However, these are outside the scope of this introductory video. Now we can define CPU load. CPU load simply tells us how much of the available interrupt period is occupied by software execution. Mathematically, it is defined as the ratio between the interrupt execution time and the interrupt period, multiplied by 100%. In this example, the interrupt execution time is 1.5 microseconds, while the interrupt period is 5 microseconds. Therefore, the CPU load is 30%. Now that we understand what CPU load represents and how it is calculated, let's see how it looks on a real digital power converter. Today I will use a synchronous buck converter regulated by a TI C2000 microcontroller. The input voltage is 9 volts and the output voltage is regulated to 2 volts. The converter operates at a switching frequency of 200 kHz corresponding to a switching period of 5 microseconds. At the current operating point, the converter is processing approximately 3 watts of input power. If you are interested in the complete software implementation, you can download the demo project free of charge from the resources section of HK Academy. For this video, however, we will focus only on understanding and measuring CPU load. I will first start a debug session which programs the microcontroller and connects the debugger to the target. Now we just click Run here. Once the debugger is connected, I simply enable the converter by setting the start converter variable to 1. As you can see, the converter is now regulating the output voltage. On the oscilloscope, we are monitoring three signals. The first channel is the GPIO signal that we will use to measure the interrupt execution time. The second channel is one of the PWM signals. And the third channel is the converter output voltage. Every time the control interrupt starts, this GPIO pin goes high. Just before the interrupt finishes, it goes low again. As a result, the pulse width directly represents the interrupt execution time. If we compare the pulse width with the interrupt period, we can immediately calculate the CPU load. Now let's look at the oscilloscope measurements. Here we can see that the GPIO on time is approximately 1.5 microseconds, while the signal period is 5 microseconds. Therefore, the CPU load is approximately 30%, exactly as we discussed on the previous slide. As you can see, measuring CPU load is actually very straightforward once you know what to look for. Let's quickly summarize what we have learned. Throughout this video, the term CPU load referred specifically to the execution time of the control interrupt. CPU load simply represents the percentage of the interrupt period occupied by software execution. It depends on two quantities, the interrupt execution time and the interrupt period. As we have seen, measuring CPU load on real hardware is actually very straightforward once you know what to observe. Understanding CPU load is an essential first step before discussing topics such as code optimization, interrupt timing, or real-time software design. If you would like to repeat the demonstration shown in this video, you can download the complete demo project free of charge from the resources section of HK Academy. In the next video, I will show you two practical methods for measuring CPU load on TI C2000 microcontrollers and discuss the advantages and limitations of each approach. Thank you for watching, and I will see you in the next video.